as we'll get going here. Hello, for those who know me, I'm Professor Spiegelman. For those who don't know me, I'm Professor Spiegelman. I am subbing for today for Professor Manley because he is off to make the world safe for democracy. He's off to actually testify in front of Congress, so I get to do his teaching. So I'm the substitute. Be nice to me. I will try, and I understand you guys are working on numerical linear algebra. You sort of started that. One of my favorite subjects. I will try not to confuse you, but I'm basically going to go through the notes from where you left off. As I understand it, last time you just started on matrix norms. Okay, so you started off with sort of the basic machinery. I'm going to go back to vector norms because they're easy to understand. Vector norms are basically a scalar measure of essentially the length of a vector. There's lots of ways to define them, but fundamentally a norm is a mapping from a vector to a real number. They have basically these three properties are all you need. It's a positive number, it's greater than or equal to 0, and it's only 0 if the vector is the 0 vector. Good. So it's the notion of length or a measure. There's always a triangle inequality, is that the norm of the sum of vectors is less than or equal to the sum of their norms. And there's a rule for scalar multiplication that this is simply the norm of take any vector times a scalar quantity. It's just basically the scalar absolute value of the scalar quantity times the norm. Absolute value because this thing, or argument, because this has to be a positive. All right, that's it. That's vector norms. That's easy. It's the length of a vector. There's where you were, I think you started last time, there was this idea of, yes? Oh, I didn't realize the CBN. Okay,
Yeah, okay.
Set it up.
Yeah, so you just turn
That's
that
why
on.
I have a nice room. Okay.
Yeah.
I knew I don't get nice rooms if I don't price.
Some price to pay.
There's always a price to pay.
So-
There we
There
go.
we go.
All right. Is that
Perfect.
good? You good? I'm mellifluent.
You're a little louder now, too.
Yes, that's not a good thing. Okay, so where were we? Oh, echo, echo, echo. Can I turn this down? Can I turn the mic off inside here, or do you need it?
Yeah, you can put that away. Just that one you're wearing.
Okay, well, I hear myself. It's very strange. Okay, so now what we want to do is extend those ideas to the norm of a matrix. And this is a slightly more complicated object, but it's the same idea. It's some notion of how big a matrix is, but more to the point, it's how it distorts its objects. A matrix times a vector is a vector. And so the fundamental definition of a matrix norm is here. We define, and this M and N, there's different flavors of norms. This is the general one. We say the M norm of A times X, okay, this is called an induced vector norm. So the idea is, I know how to take the norm of a vector, okay? How you take a norm of a matrix is less clear, but I can always take the norm of a matrix times a vector because that's a vector, okay? So the matrix norm usually says, you think of it this, actually I think of it this way. The matrix norm is the largest value of the M norm of A times X. So I take A times X, that's a vector, I take its M norm, and I divide by the length of the vector X in some N norm, okay? And then I take that over all X I can possibly do, okay? And the biggest number that I get, that's the norm, okay? That's sort of, normally when I do this, N and M are the same thing. There's a geometric picture to this which is actually useful, which is, let's see, next one here, which is if we assume that, again, I'm going to really just think of N and M as being the same. I can always choose a unit vector, X be a unit vector in some norm, that is, its norm is 1, length 1. In that case, this is a slightly simpler idea, which said that the norm of A is the maximum value, the supremum of A times X in this norm M for all vectors, all unit vectors. I look at all the unit vectors and I take them under the image A and I see how big that thing is. Okay. Now there's a geometric picture there. It comes later in the notes, but I'm going to, since Professor Manley did such a nice job making these figures, there's a geometric picture is this. This is in the 1 norm. Let's start with the 2 norm, okay, because that's actually a little simpler to see. So what it says is, what is the set of all unit vectors in 2D, in the 2 norm? What is the unit sphere in 2 dimensions? The set of all length 1 vectors is a unit circle. A times X takes every vector on that circle and maps it to something else. Okay. So this is the set of all vectors whose norm, to norm is 1. And then a times x, for the particular a that we'll look at in a little bit, is going to distort each one of these things. In this case, it's going to stretch it into an ellipse. Okay. I then look around that ellipse and I ask, what is the longest vector? What is the length of the longest vector in the to norm that under this mapping? And that's the norm of A, the to norm of A. And it's, you'll see, so these blue arrows here are, we take the unit vectors, and the blue arrows, the unit vectors map to there. They're not actually the longest ones. They're a good estimate. In fact, it's a trick you can do, is you will always know that the unit vectors 1, 0, and 0, 1 always map, are always on this. So we can always easily calculate the length of a times x of those, and those will be a lower bound. So in this case, and we'll show what it is, but that black vector is the norm of A. It's a little bit longer than what happens to the y-axis. What's more fun is you can do this in any norm. So what is the unit sphere or the unit ball in the 1 norm? The set of all vectors whose absolute values of their components add to 1. It looks like that. Okay. So always 1 and 0 and 0 and 1 are always, this is the unit sphere. It's the unit diamond, right? So so what's this one here, for example? That's a vector whose 1 norm, absolute sum of its terms, is 1. It points in the 1, 1 direction. So its units are, so this is a half-half right here, okay? In the 1 norm, that is a unit vector. People happy with how you define the 1 norm? Okay. So that's what the unit sphere looks like. When I take a times x, it maps that box to that thing, okay? And then we go around and we ask, what is the longest vector in the 1 norm? And that's the 1 norm of A. Okay. And likewise, you can do this in any of these norms. That's the 2 norm. The infinity norm looks like this. The infinity norm says the maximum value of a vector is, so the infinity norm of a vector is you just go down and you find the largest, the maximum value, absolute value. Okay. So what it means is that any vector, any unit vector in the infinity norm has one value which is 1, right? And everybody else is less than that. Okay. So it says anybody whose y value is 1 until you get out to 1, 1, and then x is the largest one. It looks like this square here. And you map that to that, and again, you find the largest one. Why do we care? So what he doesn't say in the notes just yet is the reason you're interested in the A norm is that where we're going, not today, but in the future, is this is numerical linear algebra. In classical linear algebra, your matrices are either singular or invertible, right? And you know everything about them. In the real world, things are a little more subtle. There are matrices that are almost singular. Okay, and the question is, what is a measure of a matrix that is close to being? If it's singular, it's hard to invert. Sorry, if it's not singular, but it's close to singular, you're going to have real trouble with a lot of these algorithms. Things blow up. Okay, and so the thing you're after is this idea of the condition number. And the condition number is related to the norm of a matrix and its inverse. So that's where these all are for. But now I'm just going to go back.